Hi everyone, I'm Vivek, and in this presentation we'll look into a recent work titled Recent Neural Methods on Dialogue State Tracking for Task-Oriented Dialogue Systems, a survey, which is a shared work with my colleagues Mustafa Sheikhalishahi and Bernardo Magnini at Foundation of Bruno Kessler. So the overview for this presentation is as follows. Initially, we look at the motivation for this work, followed by a discussion on what dialogue state actually is and the data and the evolution for dialogue state tracking task. And then we discuss on some of the models that are proposed in the recent years, addressing various challenges in dialogue state tracking, followed by a brief discussion on existing challenges in dialogue state tracking, and finally the summary. So the motivation for this work has been the drastic progress in dialogue state tracking task in the recent years, mainly due to the progress in neural networks architecture. And in these years, dialogue state tracking has addressed various challenges such as modeling unseen slot values for single domain dialogues, or be it for modeling multiple domain dialogues, and now even capable of performing zero shot tracking. And to the best of our knowledge, only a few works try to capture this massive progress in dialogue state tracking task, and uh, which were published in 2016 and 2017, and are fairly outdated, mainly due to the uh, progress that we have had in dialogue state tracking in the past years. And the main objective of this work is to fill this gap. So before we move on to dialogue state tracking, it's important to understand what we mean by dialogue state. So the dialogue state comprises of the summary of the dialogue history until turn T. Ideally, it comprises all the sufficient information for the dialogue policy manager to choose the right system action for the next turn. And this dialogue state is usually expressed in the form of slot value pass. An example of dialog state at turn T can be seen at the below here, where the user is looking for an Italian cuisine and the SD center area. And these slots can be of two types. One is either informable or requestable. In short, the informable slots are slots for which the user can provide values as constraints or part of the dialog goal. And the requestable slots are slots for which the user can only request information from the system. And dialog state tracking is responsible for estimating the current dialog state at each turn T. And usually the dialog state tracking is performed either at the turn level or dialog level. At turn level, the prediction for slot values is made only at the current turn, meaning only the slot values expressed in the current turn are predicted. And then using an update mechanism, the previous dialog state is updated to the current dialog state based on the current turn prediction. And this update mechanism could either be simple rules or a function that can be learned during training. And a dialog level prediction, the model takes the complete dialog history until turn T as input, and predicts the complete dialog state at each turn T. Here is a sample example of how a dialog state evolves in a dialogue. You can see that initially the user specifies the constraint price range to be moderate, and then he updates the location that he is looking for as well. And finally, he requests the address and the phone number for the particular restaurant. So these are some of the data sets that have been widely used in literature for DST task. These are not all, but these are the widely used data sets. The first is the dialog state tracking challenge dataset, DSTC 2 and 3, and then is the Wizard of Oz 2.0, which was collected using Wizard of Oz framework for restaurant domain. This is a single domain dialog dataset. Multiverse is a multiple domain dialog dataset consisting of around 7 domains. And then we have the schema guided dataset, which is also a multi-domain dataset consisting of around 16 domains. And then we have the tree DST, which is a fairly new dataset and has not been uh, used in the recent works much, but it's quite new. And then we have the machine-to-machine dataset, which is generated using user simulator. So here are some of the statistics for each of the dataset. The most widely used dataset for uh, single domain tracking models is the Wizard of Oz 2.0 dataset. And for the multiple domain is a multiverse 2.0 dataset. Sorry, is the multiverse dataset consisting of around 7 domains. And HGT is the dataset published during the Dialog State Tracking Challenge 8 task, and it consists of around 16 domains, and we can see that the number of slots is fairly high in this particular dialog, meaning showing the complexity of this particular dataset. And this dataset has been is being more widely used in the past year as well. So these are the evaluation metrics that are used in the literature for dialog state tracking models. The first is the average goal accuracy, uh, which uh, which computes the average accuracy of predicting the current value for a slot. And then is the joint goal accuracy. Joint goal accuracy is the primary metric for evaluating state tracking model. It, no, it shows the accuracy of predicting the complete dialog state at a turn t correctly. So the average accuracy goal checks if a current value for a slot is predicted correct, whereas the joint goal accuracy checks if the all the slots at a given turn are predicted correct. And then we have the F1 measure for the requestable slots, and the last is the time complexity for the dialog state tracking models. So before we move on to the models, here is uh, a sample ontology for a restaurant booking domain. This ontology is chosen to be much simple, consisting of only the slots, whereas in real world the ontology could be more complex. So here for restaurant booking task, an ontology consisting of slots could have the informable slots and requestable slots separate with the slot values names mentioned. And for informable slots, we will also have the values for each of the slots mentioned uh, as well. So it is important to note the values here, because based on this, we will group the models into either static ontology or dynamic ontology. Okay, so static ontology models are models where models predictions for dialog states are from a fixed set of values. What we mean by fixed set of slot values is that they rely on a fixed ontology, meaning that the ontology doesn't change, and the model is required to predict only on this fixed ontology. So the slot value pairs are predefined and cannot be changed once the model is trained. There are two approaches uh, to predict for slot values in static ontology. Sorry. Uh, One is using an output layer and applying a softmax as the last at the last layer to get a probability distribution over all the values, all the slot values. The other is to use a value encoder separate and compare it with the input representation and get a get a score for each of the values separately. Okay. uh, so the first approach for static ontology is the delexicalization approach. So here in delexicalization, the occurrence of slot names and values are replaced with generic tags. For example, I want Chinese food will be replaced I want value food, where Chinese is the value and food is the slot. And using such a delexicalization approach uses the model improves the robustness of the model, and it also addresses the imbalanced training data for the slot values. But this requires a more manual feature engineering, because we need to find the occurrences of values in the user utterance, and it may not be straightforward that the user uses the same value as in the ontology as in that runs as well. To address this, a data-driven DST was proposed in the following years, where a separate module named candidate representation is used to represent each of the slot value pairs, and this representation is then combined with the system output representation and the user utterance representation to get a binary score prediction, show saying if a value is expressed in the utterance or not. Okay. The disadvantage of this model is that It uses a separate candidate representation for each slot. So the later models focused on an approach called parameter sharing, where a single encoder is used for all slots, which reduces the number of model parameters, uh, uh, improves the, reduces the number of nodal parameters, and improves generalization as well. Statement was one of the first model to perform the parameter sharing approach. It combines the n-gram feature engineering with the slot representation to get the representation for the input, and then relies on the value representation uh, to get score for each of the values. So here they use pre-trained embeddings to get the value representation. Okay, and the next is regarding the latency in dialog state tracking. So the previous approach so far have used recurrent neural networks in their architecture for encoding, and GCE model initially addressed the latency in the state tracking model. So they took the state of the art at that point, which was the GLAD model, and then proposed using a single RNN instead of multiple RNNs, reducing the latency for state tracking models, which was then improved by the GSET model, which proposed using a shared encoder and feed-forward slot specific decoders, reducing the latency considerably, and also showing to outperform both the GLAD and GC in the member. Okay, and the more recent approaches to DSTG have started using the language models as pre-trained encoders, and one of the first models to incorporate language model is the SUM-BT model, which uses the BERT model as encoder, combining with multi-head attention to obtain the slot-specific input representations. So next we have the other class, the dynamic ontology models. So what we mean by dynamic ontology is that it should be able to track for new values for the slots, which the static ontology cannot do. And to perform this, one of the approaches that could be done is to either copy the slot value from the user input to the output, or generate the slot value as the output based on the input utterance. One major thing to note here is the output vocabulary difference between dynamic ontology models and static ontology models. In static ontology models, the output vocabulary is similar to the number of values for the slots, whereas in dynamic ontology models, it is the size of the vocabulary of the model itself, because here we are not sure what are the values that go in for the particular slot, and the model may have to generate new values. So two approaches that are widely used in literature for these is the copy and pointer networks, which both rely on attention mechanism to obtain scores over the input tokens and generate them at the output. One of the first models to use these approaches successfully in dialog state tracking is the trade model, which was based on a generative approach. They incorporate copy mechanism along with the slot gate, and generate the slot values for each slot. So here is a overview of uh, the trade model. We can see that we have the encoding layer here, followed by the attention mechanism, which provides us the context vector, and we have the slot gate, which denotes if a value is expressed by the user, it means none, or if the user doesn't care about the value, which is don't care, or if the value is to be decoded from the user input. So if the slot gate says to be pointer, then the value is decoded based on the copy mechanism approach. Okay. One drawback of using trade model is that it cannot predict for categorical values. So the next approach is the DS pick list approach, which uses the dual strategy approach to predict over either fixed slots or generate new value tokens. And Trippy was also proposed in this direction, using a slot key to predict first the slot values and then using a copy mechanism to predict the slot values. More details on this approach are on the paper if you're interested. So the last is the schema guided models, which proposed using a predefined schema structure to be adopted by all the domains, and this would enable doing it enable to perform transfer learning and zero shot modeling as well. We discussed on two approaches in the paper. One is the domain aware DST, and the other is the neural reading approach, where the dialog state tracking task itself is formulated as a reading comprehension task. And to summarize, there have been impressive amount of progress in modeling architectures for DSTC. And here we group models to either static ontology or dynamic ontology based models. And uh, we show a couple of takeaway points here, and much more takeaway points are available in the paper if you're interested. And thank you.